we will explore different tools to analyze the validity of our reconstructed map. So the most standard descriptor of the quality in cryo-EM is the Fourier shell correlation. When the Fourier shell correlation drops below this 0.143 threshold, and then we report that resolution, which is in a way fine as long as we all report the same criterion, so that things can be compared. But this number shouldn't be taken blindly. So let us see a few problematic examples. So I have taken this map from EMDB, so this is 31817. So let's look at the map. So the map, the resolution deposited or declared at the databases is 5.1 angstrom. But you look at the structure, this structure doesn't have, it is actually, I think it is negative staining, so it doesn't have 5.1 angstrom, even if the claimed resolution is that one. So remind, FSC is you repeat the process twice and you compare the two results. If you are very consistent in your processing, then your two structures will be consistent up to very high resolution. But this doesn't have a 5.1 angstrom, even if the FSC declares that. Okay, so here we will use deep res. That is an algorithm based on neural networks that a protein structure at different resolutions, it has different properties. So it compares the properties of your map to the properties of the expected, to the expected properties of a protein at that resolution, and then it assigns a resolution to every voxel. So we see that 5.1 is not, it is at the extreme of the local resolution distribution. Actually, this is a very general result. So the resolution of the FSC is at the extreme of the local resolution histogram. So the kind of cartoon way, but we can think of the FSC resolution as the best resolution of the best voxel in the best direction. So it is an indicator of up to where you have gone. But here in this example, this very high resolution has been caused by these oscillations that are high frequency. So we see here high frequency oscillations that might be consistent between the two halves, and those are the ones that have been detected by the FSC. So so here the histogram says, okay, it is 12 something or even 13 something. So it is very low resolution. There is some peak around 7, but this is not coming from the structure, but of these artifacts around. And so don't believe blindly the 5.1 angstrom, the FSC resolution. Okay, so this is one. Let me close everything. Okay, so another example. So this is 14,080 from EMDB, and here let's look at the map. So when you look at the map, it has been filtered, it has been masked. So it has been masked to very, very, very tight mask. So fortunately they have deposited the two halves, so we can compare this half. So I have imported the two halves independently. So if we go to a similar slice, so this is this slice. So yeah, you see a lot of details, but having the noise around will help you to check what is really the resolution of your structure, at least in terms of signal to noise ratio. That doesn't mean that it is a true biological meaning. So when we say I have reached 3 angstroms resolution, what you have is a signal to noise ratio of 3 angstroms, but that doesn't mean that the signal you have reconstructed really represents a macromolecule. So part of the analysis we will do with these halves, where they look like what they should. So what is the right structure? So what is the structure and the reconstruction, the quality that we have been able to reconstruct? And this one we will see that it is a bit artifactual because of the tight mask. So when you apply a mask to a signal, the mask in Fourier space, the Fourier transform of the mask is convolved with the Fourier transform of the signal, and then you are artificially creating a correlation in Fourier space. Okay, so let's take the masked map, and we will analyze the local resolution with deep res. So the local resolution looks like this. So it is they were claiming 4.2 angstroms. This says that it is 3.2 or 3.4 or something like that. And the reason is that deep res is fooled by we can see this. This is very nice. We are fooled by the mask, because it really looks like having very sharp details, but these sharp details are caused by the masking. So yeah, so if we apply the deep res to to the half map, now the resolution drops from 3 to 5. So now it looks more like a 5 point something reconstruction. So the mask really influences a lot all your measurements of resolution. And also monores, for instance, that is another local resolution analyzer. So it is also fooled by the masking. So the masking, because monores looks at what is the signal compared to the noise, and the noise is defined as the background. So if there is no noise in the background, your signal appears to have extremely high resolution. So actually this one is almost reaching Nyquist, but it is because of the mask. Okay, so now let us import the two halves. So now, even if they are halves, so if you combine them, you will get a better reconstruction, but this better reconstruction is not so much better than the original two halves. So you reduce the power of the noise by factor 2, which is an important factor, but it is not a factor 10, if you want, or a factor 100. So we can compare the resolution between these two, the FSC between these two. So the FSC between these two is 5.3. So yeah, so it seems that this claim of 4.2 is an overstatement of the underlying correlation. So if this is happening because of this masking, when you apply a mask to a structure, you're correlating the Fourier coefficients in Fourier space, and then they correlate much better. So it seems that it is a 5 point something angstrom that is consistent with what we were seeing here of the local resolution. So the local resolution identified, but it needs the noise around, otherwise it cannot make a proper comparison. Then we can if you have an atomic model, then you have other ways of checking the quality of your map. So here we are importing the atomic structure, so 7K EC. So we can analyze this map and and PDB put together. So what we see is that the origins are not the same, and even they are turned upside down, you see. So this is the upper part of this map. So yeah, so they are not in registered, they're not registered. So you can take the map, you can take the structure, and you can fit them at 3 angstroms. So now, after fitting, now we have found, or Phoenix has found the correct transformation, and now they are both on the same place. So now they are both in the same place. Okay, so now from now on we can analyze and compare this PDB to this map, and you can have multiple tools for that. So here you have the validation tools that we have for when you have a PDB and a map. So here are a few of them, and if you go to single particle analysis, also you have post-process, it is analysis, and then validation. Also you have multiple possibilities. So these ones are purely based on the map, and the other ones are based on the map and PDB. Okay, so let's look at the analysis of this one. So the validation criterion of Phoenix, and we can see, for instance, this report is very rich, so you can spend a lot of time looking at all the small details of the report. So how many, this is exclusively about the atomic model, and then you have about the map. So it has some reports about the map, and some FSCs at different levels, and also map versus PDB, and then you have all kind of cross correlations, and you can go for mole probability. So this is analyzing the PDB alone, and you can have, for instance, which are the outliers according to Kablam. So Kablam says this residue is disfavored, this is a geometrical outlier, this is an outlier of Kablam, and so on. And then you can go to model versus data. So in the model versus data, we can see again all the correlations. We can see these correlations by chain. So you take chain A, and now you can see, no, this is cross correlation per chain, but also you can see it by residues. So you take chain A, and then you see, okay, this is the correlation of the map versus the model at the different residues. And also you have all kind of FSCs here, and map resolution estimates. So there are a few of them, and you see that it is quite variable. So you have values from 2.4 to values of 8. So the number that you choose, it is really important. So it is not written in stone, that number is measuring mostly consistency of your process. And for instance, here if we compare the FSC of the map with the model, we see that it is somewhere between 7 and 8 angstroms. So below that they don't correlate. Actually, this is an important point here. So the 0.143 threshold that we normally use is when you compare two half maps, and this threshold is computed trying to imagine what would have happened if I combine the two half maps and I compare to the original signal that is noiseless. And if I'm comparing a map to a signal that is noiseless, the threshold is no longer 0.14, but it is 0.5. That is why this line is highlighted here. Okay, because here we are comparing a map to a PDB model. So yeah, we all like to report the highest resolution number ever, but we have to be careful with what is the actual agreement and the actual biological content of our reconstructed maps. So with this, I will close this project and see you in the next one.